Recording. So when we last left off, we talked about reactions to prepare esters, amides, thioesters, and a range of carboxylic acid derivatives via carbonyl substitution reactions. So what we're now going to do is we're going to talk a little bit about esters and ester nomenclature and sort of complete our series where we've named all these different carboxylic acid derivatives. So esters are derivatives of carboxylic acids, and they require a bit of a unique numbering system because you have both a carbonyl carbon and an alcohol carbon. So first we number the carbonyl carbon as carbon number 1. Next, you note the alkyl chain attached to the carbonyl carbon. From here, then we number the carbon attached to the ester alcohol oxygen as carbon 1. Then you note the alkyl chain attached to the alcohol oxygen. We then name the alcohol alkyl chain first. Then you name the carbonyl group alkyl chain, replacing the suffix with the O8 suffix. Okay, so we have a propyl group, so we'd name this as propyl. And then we have an ethane chain, so we'd name this as propyl ethanoate. So ethane turns into ethanoate. Does that make sense to everyone? So you name the alkyl chain on your alcohol, then you name your carboxylate chain, modifying the ending to the O8 ending to denote the fact that we have an ester. Any questions on this naming convention? Okay. So looking at this next case, in the event that we have substitution on our alcohol side chain, we name this alcohol side chain just like a normal alkyl chain. So this would be 1-chloro. So 1 carbon chain. So we denote it with methyl. And then we have a 3-carbon chain. So rather than propyl or propane, we name this as propanoate. Does this idea make sense to everyone? Really, it's best to treat esters as they show structurally as an alcohol and then a carboxylate component. In this next case, let's look at what happens if we have substitution at the carboxylate side chain. So we name our first alcohol chain as methyl. That should be chloro. So we have a propyl chain. The chlorine group or chloride is at carbon 2. So we name this as methyl 2-chloropropanoate. Notice how the alcohol side chain and the carboxylate side chain each have their own unique numbering convention. Does that make sense? Any questions on these naming conventions? Okay, so let's try to practice what we've learned, and we have 2 compounds, A and B. And let's try to name each of these compounds following IUPAC nomenclature rules. So let's take a few minutes to work through these examples. And if there are any questions that I can address, don't be shy to ask them in the chat or verbally. And it would be great to see student proposed responses shared in the chat, verbally, or annotated directly onto the class whiteboard. So we have a 4-carbon chain. Okay, for our carboxylate chains, we have a lot of students typing butanoate. Okay, how do we name this 4-carbon alcohol chain? So you're correct, it's a butane chain, but we name it like a substituent. So this will be butyl butanoate. Does that make sense? Okay. So let's try to apply what we've learned now, and let's continue naming these ester compounds by working on examples B and C. And again, I'd love to see some student responses shared in the chat or verbally. So, does anyone have a proposed name for any of these compounds? So we have a proposed name for B. So we've identified the alcohol side chain as 1-methyl propyl. Okay, and then we have a 4-carbon chain, which is butanoate. Yeah, that proposed name looks reasonable to me. Does anyone have an alternative IUPAC name for this compound? What does this substitution pattern, is there a formal name for this particular substitution pattern? Where we have a butyl chain with substitution at the secondary position. Sure. Is there a condensed name similar to like isopropyl, right? Is there a name similar to isopropyl? This side chain? Would anyone like to look over their notes and try to propose an informal name? Yep, seek butyl. You can also call this seek butyl butanoate. No worries. You can use either convention, but I'm just trying to note the fact that there are also condensed names for many of these side chains. I personally prefer the long form IUPAC names because they're easier to parse following our numbering and naming conventions. But I just wanted to highlight the fact that this is a seek butyl group and we've seen them before. So you're welcome to use that naming convention when you're naming the alcohol side chain for many of these esters. Just like in lab, we prepare isopentyl acetate. Okay, so let's keep going now and let's work on example C. So this one we have substitution on the alcohol side chain, and we have substitution on the ester side chain, or the carboxylate main chain. So let's take a few minutes and let's work through these examples. And then I'd like students to share their proposed responses in the chat, verbally, or annotated directly onto the class whiteboard. So let's keep working through. It's not quite a cyclic group due to the fact we have this carboxylate carbon. So it'll probably be easier just to name it using the locant number method. So we have a 4-carbon chain, right? And then we can just name the substituents for this carboxylate side chain. Sure, so we have a proposed name of 2-methyl butanoate, okay? Butan-2-il is typically used when you're naming an alkyl group as a formal side chain off the main chain. In this case, since the 4 carbons of the main chain include the carboxylate carbon, you'd name this as 2-methyl butanoate to denote we have a methyl group at the 2 position and our main chain is a 4-carbon carboxylate. We have another student proposing the name for this alcohol side chain as 2-ethylchloro or 2-chloroethyl. Perfect. 2-chloroethyl. No worries. So we have 2-chloroethyl for this alcohol side chain, 2-methylbutanoate for the main chain. So we name this as 2-chloroethyl, 2-methylbutanoate. Does that make sense to everyone? Any questions on these examples? If not, let's talk a little bit about how esters are prepared. Esters are traditionally prepared from carboxylic acids. There are a few ways to do this. You could use the Fischer esterification. You can alkylate a carboxylate. Oh, sorry, there was a question. Yes, please go ahead. Yes, please go ahead.
If it was an isopropyl connected to on the right side, sorry, my brain isn't working today. If there was an isopropyl group, would it be an isopropanoate, or how would that be?
So generally it's preferable to use the condensed name only for the alcohol side chain, because in that case it's named like a substituent. Does that make sense?
Okay, that makes sense.
Yeah, because the carboxylate group is attached and counted for the carbon count, it's not common for you to say, like, for example, we would call this ketone like an isopropyl ketone. We're naming this isopropyl group as a substituent. When we start to count the carboxylate carbon as part of the main chain, then it's hard to name these structures as using a condensed name without losing a bit of the information for where the substituents are located. For the alcohol side chain, you have a lot more freedom. So for example, if you have something that looks like this, then you can certainly name this as isopropyl 2-methyl butanoate. Because traditionally, this alcohol side chain, we're only counting the carbons as part of the side chain. There's no extra carboxylate carbon to worry about. Did that answer your question? Perfect. When in doubt, just use the locant number method, and esters, the names will be pretty straightforward for naming just the alcohol and then the carboxylate chain and then putting those names together. Okay, so we've already talked about many methods to prepare esters. So one method is via direct carboxylation and direct alkylation of a carboxylate salt. So if we have a typical alkyl halide, it can react with a carboxylate salt to yield an ester. However, your alkyl halide must be primary. This is a textbook SN2 reaction. You can get away with secondary, but it's a little iffy. The other method is Fischer esterification. However, because it's under strongly acidic conditions, your alcohol generally must be primary. So the first method is, so in terms of the two methods outlined, acid catalyzed transesterification, that's known as the Fischer esterification. The alkylation of a carboxylate salt is also another common method. You can think of it very similar to the Williamson ether synthesis in terms of the actual reaction pathway, in terms of the substrate tolerance. Just like the Williamson ether synthesis, alkylation of a carboxylate salt generally requires a primary or secondary alkyl halide. Did that clarify? Perfect. Now, again, just to reiterate, the Fischer esterification, we're also limited in terms of the character of our alcohol, in that we generally only can use primary alcohols. So we're limited in terms of what side chains we can have on the alcohol side chain. An alternative method that's much more general is to convert your carboxylic acid into an acyl chloride. From here, it can react with functionally almost any alcohol to yield a complex ester. So this last method is probably the most general method to prepare a range of structurally diverse esters from carboxylic acids. It's a little more steppy, but in exchange, you can use a wide range of alcohols for this esterification. Does this discussion make sense to everyone on the benefits, merits, and substrate requirements for each of these three reactions? Perfect. So let's keep going now. And let's talk about the counterpart to esterification, which is hydrolysis. So as we talked about in the Fischer esterification, if you use an excess of water under acidic conditions, an ester can be hydrolyzed under aqueous acidic conditions to yield a carboxylic acid plus an alcohol. You can also use strongly basic conditions, and we'll show the mechanisms for each. Let's start off with the acidic conditions. So under acidic conditions, what's the first thing that's going to happen to this ester? So following our idea, following our manifold for typical carbonyl substitutions under acidic conditions. So this is the reverse of the Fischer esterification, and this is known as hydrolysis. And just like any acid catalyzed carbonyl substitution, we're going to protonate our carbonyl oxygen to activate our carbonyl carbon and make it more electrophilic. This mechanism is the exact reverse of the Fischer esterification. Now that we have this activated carbonyl carbon, water can attack Now, what we're going to do is we're going to engage in a series of proton transfers. And these proton transfers are going to activate our alcohol, so we can lose this alcohol group. And it's going to free up a lone pair on our oxygen atom. So now that we've activated our ester alcohol as a leaving group, we're now able to kick out our leaving group to give our carboxylic acid. Now you may notice I'm drawing each of these steps with equilibrium arrows. This is deliberate, and this is to note that depending on whether you have an excess of water or an excess of alcohol, you either get the ester or the carboxylic acid. It's the exact same theory as the Fischer esterification under acidic conditions. For our last step, we're just going to pull off a proton. And that gives us our desired carboxylic acid. Does everyone see, and does this remind everyone of the Fischer esterification? As we talked about for that reaction, if we use an excess of water, the Fischer esterification goes in reverse and you get the carboxylic acid. This is known as ester hydrolysis. Well, that's because played in the forward direction, that's hydrolysis. In reverse, that's the Fischer esterification mechanism. Actually, almost step by step. If you reversed all the arrows, you'd get the Fischer esterification mechanism. Any questions on acid catalyzed hydrolysis? Yes, exactly right. This is an equilibrium. And so if we have an excess of water, hydrolysis is favored. If we have an excess of alcohol, or if we remove water, the ester is favored. Does that make sense? Essentially, you can view it as the forward progress to the carboxylic acid requires water. The reverse progress to the ester requires an excess of alcohol. A classic application of Le Chatelier's principle. Okay, now let's talk about a little bit more of a boring mechanism, and this is the base catalyzed mechanism. So we have our ester, and if we treat it with sodium hydroxide, hydroxide will just immediately attack the carbonyl carbon. It's technically in equilibrium, but not by much. From here, we make a tetrahedral intermediate, and then we kick out alkoxide to generate our carboxylic acid. And just to note, part of the reason why this reaction practically goes in one direction is because the moment you kick out alkoxide, you actually end up protonating the alkoxide ion, and in turn, you make a much less effective nucleophile. Does this base catalyzed mechanism make sense to everyone? And does everyone see how we cut down on our nucleophile strength during this protonation step? Yes, yes. Perfect. Okay. Oh, yes. Yes, that's true. Typically, these are run using an excess of sodium hydroxide in water. And because the carboxylic acid is so appreciably acidic compared to everything else, it will typically protonate any alkoxide ion present. You do get a little bit of alkoxide ion generated via proton transfers with hydroxide, but the main key interesting part for this reaction is that you make the carboxylic acid and then it quenches out your leaving group and makes it less reactive as a nucleophile. And that helps drive this hydrolysis reaction to completion. Perfect. So just a recap for this acid catalyzed ester hydrolysis mechanism. The first step in any acid catalyzed mechanism is activation of our carbonyl via protonation. Then our nucleophile, in this case water, attacks. From here, we'll pull off a proton and engage in a series of proton transfers. This frees up a lone pair on oxygen and activates this alcohol as a leaving group. From here, we can kick out our leaving group, and that gives us our protonated carboxylic acid, which is quickly deprotonated to yield our desired neutral and isolable carboxylic acid. Does this mechanism refresher make sense to everyone? Any follow-up questions on this mechanism that we didn't address in the earlier example? Okay. In the case of base catalyzed ester hydrolysis, for our first step, our nucleophile attacks the carbonyl carbon. We kick down a lone pair and lose alkoxide. From here, our carboxylic acid, which is highly acidic, is deprotonated, and we get a carboxylate ion. One other point that I'm going to be more explicit about in this recap is that looking at this leaving group, if we can call it a leaving group, is O2 minus even a remotely reasonable leaving group? Does that look like a good leaving group at all? No. So generally, this is why carboxylic acids are quite difficult to substitute under basic conditions, because you'll deprotonate your carboxylic acid and now you're left with this carboxylate ion with a terrible leaving group. It's even worse than amides. Carboxylic acids under basic conditions almost never engage in substitution reactions. Does this make sense to everyone? Okay, so let's keep going then. So in this case, we're asked to do a series of product predictions. So in this case, we're asked to predict the product for each reaction and draw a mechanism for each reaction. And there's plenty of space below on the class whiteboard if you'd like to try to annotate and share your proposed mechanisms. So in this case, we have an ester treated with sodium hydroxide and water. Hydroxide's immediately going to go after the electrophilic carbonyl carbon. And then from here, the tetrahedral intermediate will collapse and kick out alkoxide, We have another student taking an attempt at this second example. In this case, our carbonyl oxygen's protonated. One thing is that if you're protonating, the source of electron density goes to the electron deficient atom, so it would be the other way. No worries, no worries. So we have our protonation step down. Okay. Now, just like before, our water or hydroxide equivalent will attack the carbonyl carbon. And in both examples, we're getting this tetrahedral intermediate. And eventually, we're going to kick out the alcohol. So both of these mechanisms are looking completely reasonable. Now we just need a quick proton transfer step to advance each of these mechanisms. Perfect. So we're pulling off a proton in the top example from the carboxylic acid, and in the bottom example from the highly acidic alcohol. Now, we eventually want to kick out this ester side chain. So how do we activate that side chain as a leaving group? How do we activate that side chain as a leaving group? We protonate it. Exactly right. Perfect. Now that we've activated our alcohol as a leaving group, we can kick out our ester alcohol. Oh, no worries. I was just including the alkyl side chain, but I see you're just about to do that. So now that we've activated our alcohol, can we kick out the alcohol to get our carboxylic acid? So we have this activated leaving group. So let's kick out our leaving group. Yep, exactly right. And from here, we have our protonated carboxylic acid. And that is just one step away. But the mechanism that was drawn so far by the students looks great. It's all perfect. From here, now now that we have this protonated carboxylic acid, all we have to do is pull off a proton and we get our final desired product. Perfect. So it's great to see students sharing their proposed responses, and both of these mechanisms looked great. So let me just re-annotate them. So we'll start with the base catalyzed mechanism. So in the first step, hydroxide will attack and we'll get a tetrahedral intermediate. And I find the moment you start putting pen to paper is when you can begin to notice and start to ask questions about the content that may not have been immediately apparent at first glance. So after this tetrahedral intermediate collapses, we have a carboxylic acid, but that carboxylic acid is highly acidic. So it's going to immediately get deprotonated by hydroxide, and that gives us our carboxylate anion. And that's what sits around in solution until the reaction is quenched. Does this first mechanism look reasonable? Perfect, perfect. Okay, so let's take a look at this acid catalyzed mechanism. In this case, we are trying to convert our ester into a carboxylic acid. Just to reiterate what the students proposed, we'll protonate our ester carbonyl. From here, water will attack. Then we'll have a series of proton transfers. That in turn will give us our activated leaving group. And from here, we'll kick out our activated leaving group, and that will give us our carboxylic acid, which can be isolated as the neutral carboxylic acid after deprotonation with water. Do these mechanisms make sense to everyone? Oh, okay, sure. Is that good? Okay, perfect. So let's keep going then, and let's talk about another somewhat useful reaction, which is the amenolysis of esters. So esters can react with ammonia and other primary or secondary amines to form amides. In terms of the mechanism for this reaction, this is a textbook carbonyl substitution under basic conditions. So in the first step, our nucleophilic amine attacks the electrophilic carbonyl carbon. From here, we end up generating a tetrahedral intermediate. From here, we'll kick out our leaving group. Now, likely ammonia will pull off this proton before anything else happens. But you can certainly draw the loss of the leaving group, and that's a perfectly reasonable step to propose. Because we're under basic conditions, it would be weird to have a protonated amide. Well, a protonated amine, pKa of around 9, it's a little more reasonable to have floating around in solution. So from here, we'll kick out our alkoxide leaving group, and that gives us our desired amide. Does this mechanism make sense to everyone? Any questions? Okay, so let's keep going then. And let's talk about another common. So we have a student asking, what happens to the alkoxide ion? Well, when it's floating around, it's likely just going to be protonated, not necessarily by ammonia, but by ammonium. Sure. Yes. And that's part of what helps drive this reaction to completion. Okay, so let's talk about another reaction of esters. We can convert esters into alcohols via reduction with lithium aluminum hydride. Remember, lithium aluminum hydride is selective for carbonyl functionalities, and it's quite a useful method to reduce carbonyls into their parent alcohols. In terms of the mechanism, this can be thought of as a series of carbonyl substitutions. Hydride attacks the carbonyl carbon. We make a tetrahedral intermediate, which then collapses to give our aldehyde. This aldehyde, of course, does not stick around for very long. And this aldehyde would immediately be reduced and reacted with a second equivalent of hydride to yield a primary alcohol. We've seen this mechanism in earlier chapters. Does this recap look familiar to everyone? Okay, so let's keep going then. If we wanted to isolate the aldehyde, we have a trick for that. It requires using diisobutyl aluminum hydride, also sometimes colloquially called dibal. Like the main feature of dibal is due to its substantial steric hindrance, and due to the fact that it's designed where each equivalent only has one functional equivalent of hydride. This allows you to control the chemoselectivity and mitigate overreaction. So dibal, the mechanism is identical to the general mechanism for the reduction of esters. The interesting thing about dibal is that due to its hindrance and due to the fact that it only has one equivalent of hydride to donate, if you add the dibal slowly and you control the reaction temperature, you can get selectivity for monoreduction, and you can actually isolate the aldehyde quite cleanly. Does this mechanism and does this reagent look familiar to everyone? Perfect. So let's keep going now. Similar to reduction, we can also attack esters with other hard nucleophiles, such as Grignard reagents. As we talked about all the way in the chapter on alcohols, we can prepare symmetrically substituted alcohols via addition of two equivalents of Grignard into an ester. Just as a recap on this mechanism, if we have an ester, your first equivalent of Grignard will attack the ester carbonyl carbon, and this gives us a tetrahedral intermediate. Now, we will never kick out this alkyl group. Carbon anions are terrible leaving groups. So instead, we kick out our alkoxy group. This gives us our ketone. And I have a question for everyone. Does this ketone stick around? No, a ketone is orders of magnitude more reactive than an ester. So in solution, it will preferentially react with your Grignard reagent. That's why you need an excess of Grignard, because this second reaction is unavoidable. This in turn gives us the addition product, which is this alkoxide ion. And then you can quench your alkoxide ion with H3O+, and that gives you your isolable alcohol. If you only use one equivalent, you'd get a mixture of the ketone and the alcohol. It wouldn't be selective. Any other questions on this mechanism? If you really want to get the ketone, you're better off going through the nitrile. Or you can go through the acyl chloride and use an organocuprate reagent, or you can use a complex amide derivative. So there are ways to get the ketone. The nitrile is the easiest at first glance. Does this make sense to everyone? Does this reaction look familiar to everyone? Perfect. Okay, so let's keep going then. And let's talk a little bit about how amides are prepared. So amides can be prepared typically from acid chlorides. That's the most convenient method that's tolerant to a range of substitution patterns on our starting amine. So typically you start with an acid chloride and you can react it with a range of amines to get the corresponding amide. This is a textbook carbonyl substitution reaction. I can draw the mechanism out just for everyone's reference. Your amine attacks. We get a tetrahedral intermediate. We kick out our leaving group. And then we have a cleanup deprotonation step, where probably another equivalent of amine or an equivalent of added base comes on in and pulls off a proton. Does this mechanism look familiar to everyone? Does this mechanism make sense? Perfect. Perfect. Okay, so just like esters, amides can be hydrolyzed under aqueous acidic or aqueous basic conditions. In the case of acidic conditions, the first step is our amide is protonated. I would note that for amides, it's really important to acknowledge that the oxygen of an amide is quite electron rich. That's why we often see protonation at oxygen over preferential protonation at nitrogen. From here, your carbonyl carbon's now activated and can be attacked with nucleophiles such as water. From here, we're going to see a series of proton transfers to activate our amine and to free up a lone pair on oxygen. Now that we I don't understand the question. In this case, I mean, if you use an alcohol instead of water, yeah, you can get an ester. Yes. Yes, that is possible. We're just looking at hydrolysis because that's a more common operation. So after a proton transfer, we've activated our amine as a leaving group. So we'll lose our ammonium ion leaving group, and that gives us our desired carboxylic acid. And interestingly, because ammonia is produced as our leaving group, and because we're under acidic conditions, we protonate ammonia, and now it's no longer a viable nucleophile. Does this mechanism make sense? Let's look at basic conditions. In this case, our nucleophile immediately attacks the carbonyl carbon. We get a tetrahedral intermediate, and then we kick out our leaving group. From here, we have a carboxylic acid, but it gets immediately deprotonated by our generated amide anion. And that gives us our isolable carboxylate ion, which is converted to the carboxylic acid during the quench step. Does this basic mechanism make sense? Perfect, perfect. So let's try to practice what we've learned, and let's try to predict the product from the following reactions and draw a mechanism for each reaction. So we're treating an amide with sodium hydroxide and water. These look like acidic or basic conditions. Basic conditions, exactly right. And so our nucleophile is immediately going to go straight for the electrophilic carbonyl carbon. And that gives us a tetrahedral intermediate. From here, the tetrahedral intermediate will collapse and kick out our leaving group. As our last cleanup step, as we're working under basic conditions, and because we have this basic amide anion floating around, it will quickly go and deprotonate our carboxylic acid. Perfect. And that gives us the carboxylate ion. Sure. You can draw it that way, though it's typically common to separate the loss of the leaving group and the protonation step. Now, these student proposed mechanisms look completely reasonable. So let's clear those annotations. Oh, and I'll redraw them so that way they're saved as part of the instructor key. So first things first, your nucleophile will immediately attack the electrophilic carbonyl carbon. From here, we'll kick out our leaving group. That gives us our carboxylic acid, which under the ambient reaction conditions will immediately get deprotonated by our amide anion. And that gives us our carboxylate salt. Does this mechanism make sense to everyone? Water is not sufficiently acidic to protonate the salt. Just thinking about pKa, the pKa of water compared to the pKa of a carboxylic acid, the carboxylic acid is way more acidic. Does that make sense? It's just there as a solvent because you can do like sodium hydroxide in THF. That would also work. But I find that water is such a nice solvent to use because it's so inexpensive that it's commonly used because it's also the conjugate acid of hydroxide. So if any of the hydroxide gets quenched, it's not as much of a deal. It's mainly just for efficiency considerations. You can do sodium hydroxide in THF. Many of the polar aprotic solvents don't play nicely with concentrated base and strong hydrolysis conditions, and water you can heat to high temperatures without much worry. But you can certainly do this in THF or any other solvent that your compound dissolves in. Many of these amides are somewhat polar, and so they dissolve in aqueous or highly polar solvents. You certainly don't want to do this in dimethylformamide or anything like that, because that's an amide and that'll get hydrolyzed and you'll get a mess. Does that discussion of solvent choice make sense? Perfect. Okay, so let's try to apply what we've learned now, and let's look at this acid catalyzed amide hydrolysis reaction. So in this case, we're treating this amide with hydrochloric acid in water. And we have multiple students annotating, and they both got the first step perfectly correct, which is protonation. From here, now that we have our protonated amide, it's now activated for reaction with nucleophiles. So even weak nucleophiles, such as water, will immediately go after the electrophilic carbonyl carbon. From here, water will attack the carbonyl carbon. We'll get a tetrahedral intermediate. Now, before we just kick out our amine leaving group, we have to engage in a small set of proton transfers. After a series of proton transfers to free up a lone pair on our alcohol oxygen and to protonate our amine to convert it into a much better leaving group, ammonium, we can then start to kick out our leaving group and generate our protonated carboxylic acid. From here, we can kick out our leaving group. So now that we have this wonderful leaving group in the form of ammonium, how do we get our carboxylic acid? I saw a few arrows drawn for that. Would anyone like to complete this annotation? Sure, perfect. And that way we kick out our leaving group, and that gives us our desired carboxylic acid. Perfect. So these student proposed mechanisms look completely reasonable. So let me just redraw those mechanisms as part of our instructor key. Okay, so we have our amide. The first step under acid catalyzed conditions is protonation of the amide to activate our carbonyl carbon. From here, water will attack the electrophilic carbonyl carbon. Now, in order to activate our amine as a leaving group, we're going to engage in a series of proton transfers. First, to protonate the amine and to deprotonate the alcohol. From here, we've now activated our amine as a leaving group. So then water will pull off a proton, will kick off our leaving group, and that will give us our desired carboxylic acid. The student proposed mechanism looked completely reasonable. Are there any questions on this reaction?
Is it only the forward arrows for this reaction? Or would it be
It's technically an equilibrium, but since we're drawing a mechanism where we're using an excess of water, that drives the equilibrium towards the product.
Oh, okay, that makes sense. Thank you.
Mm-hmm. Yeah, you can also collapse this tetrahedral intermediate and then deprotonate. That's also more than okay. Perfect. So let's keep going now. And let's talk about reduction. And let's just review the reduction of amides to make amines. lithium aluminum hydride reduces amides to the desired amine. And this is specific for amides and matches and mirrors the mechanism for nitrile reduction. So in this mechanism, hydride attacks the electrophilic carbonyl carbon. And because aluminum is a reasonably strong Lewis acid, we can coordinate our alcohol and activate it as a leaving group, even under basic conditions. We kick out our alcohol to make an imine, or more correctly, an iminium ion, which is then attacked with a second equivalent of hydride to yield our desired amine. Does this mechanism make sense to everyone? It's almost identical to the nitrile reduction mechanism. Any questions I can address before we try to apply what we've learned? Okay, let's keep going then. Now, you may say, what's so special about this amide reduction procedure? Well, we can prepare amides and then reduce off the amide carbonyl to make complex cyclic and acyclic amines. So reduction of cyclic amides, also known as lactams with lithium aluminum hydride, cleanly yields cyclic amines. This is a counterpart to the method of reductive amination that we observed on the exam and that we observed on the chapter on imines and enamine reactivity. So does everyone see the synthetic utility of this method? It allows us to form carbon-nitrogen bonds using methodologies that we've already established to prepare amides. And we know that it's easy to make these carboxylic acid derivatives while making amines, especially highly substituted cyclic amines, requires a few more considerations. Does this synthetic utility make sense to everyone? We can take any amide and convert it to the amine. And that allows us to get a lot of structural diversity out of the reactions that we're already familiar with. Any questions? Okay, so let's keep going then. So in this case, I'd like us to predict the product of the following reaction and draw a mechanism for this reaction. So in this case, we're treating an amide with lithium aluminum hydride in diethyl ether. So this is a textbook amide reduction with your classic hydride donor. And for this mechanism, we have students predicting that we'd get the desired amine. Yep, that's reasonable. But there's something I'm looking for particularly when we draw the mechanism, and I'd like you to show how the alcohol is activated as a leaving group. That's something that it's important to note because it explains why this reaction is selective to make the amine over the alcohol or other derivative. And it explains why the carbon-nitrogen bond is preserved. So as the student's drawn, reduction of our amide carbonyl carbon occurs readily. From here, our alcohol is activated by coordination of aluminum, and we can kick out our alcohol leaving group to make an aminium ion. From here, this activated aminium ion can be reduced a second time with a second equivalent of lithium aluminum hydride. That in turn gives us our desired amine. Does this make sense to everyone? Perfect. So the student proposed mechanism looks completely reasonable. So let me just re-annotate it for our reference. So reduction of amides is special in that this carbon leaving group bond isn't broken. We're in fact kicking out our oxygen atom as a leaving group. So our hydride equivalent will attack the electrophilic carbonyl carbon. From here, coordination with aluminum activates our leaving group. And we can lose our alcohol leaving group. From here, we now have our aminium ion, which can be reduced with a second equivalent of lithium aluminum hydride. To yield our desired amine. Does everyone see how amide reduction is fundamentally different than reduction of esters? Does everyone see why amide reduction has a unique quirk associated with it? And this stems from the fact that we can make a reasonably stable aminium ion while making an oxonium ion is not particularly plausible for esters. Amide is not the best leaving group, but this coordinated and activated alcohol can be kicked out quite easily. Any other questions on this example? Okay, perfect. So we've finished up chapter 21, and we'll start chapter 22 on the next scheduled lecture session. Any last minute questions I can address before we archive today's recording? Okay, so we'll archive today's recording.